We've learned before that calculus in the science of studying calculations. Calculus comes from the word calculation. Okay, so what does it study, or what does it calculate? It calculates, or it studies the change. Okay, you learned in Math 1 that there is something called differential calculus. And you learned that there is a term called the differentiation, or the differential, or dy by dx. Do you remember what was the physical meaning of the differentiation, or dy by dx?
It's the rate of, when the curve is like this.
Yes, when I have a curve like this. So what is dy by dx? It is the slope of the tangent.
The slope of the tangent.
Yes, the slope of the tangent. And what does the slope of the tangent mean for us? It means the rate of change. Okay, so it has a significant meaning for us, which is the rate of change. It calculates how does the changes, the rate itself. Does it change quickly like this, or does it change slowly like this? Okay, for this function, for example, we have a slow rate of change. That's why the dy by dx in this case, it will be a low value. For this will be a high speed change. This is a high speed change, so it will have a large value. So in this case, for example, dy by dx will be equal to 100, for example. For this case, dy by dx will be 0.1. Okay, as long as the dy by dx it approaches 0, or it is near to 0, the change will be negligible. It will not change. Okay. What if dy by dx was negative 100, for example? What does this mean for us?
I think it's going to be down.
Yes, the negative sign means that it is decreasing instead of increasing. The change here, it is decreasing. Okay, and this, so we have a sign, and we have a value. The sign determines whether it is increasing or decreasing. For a positive value, it means that it is increasing. Negative value, it means that it is decreasing. And the value states whether it is the rate itself. Is it high rate, or is it quickly? The change happens quickly, or it happens slowly. Okay, so these are the meanings, or the physical meanings of the differential of the dy by dx, and it is the same as the slope of tangent. Okay, so that was the mean significance of differential calculus. There is another part of calculus which is called integral calculus. And that is the topic of study of the Math 2, or the second term. What is integral calculus? You will learn now that integration, we will have an operation called integration, which is the inverse operation of differentiation. How did we find that the inverse operation of differentiation is significant or is important to us? We will know that in the lecture now. Okay. We will learn that integration means, as the differentiation meant the rate of change, integration means the area under the curve. So if I have some curve like this from A to B, I will say that integration from A to B for f of x dx, this is exactly the value of this area. This is that area, the area under the curve. Why is the area significant to us? The area is important, and it has many applications. For many applications, we need the area under the curve. as we needed before the slope of tangent, we will also need the area under the curve. Why? I will tell you in the next, in this lecture. Okay? First, if we need to find the area under the curve, okay, for some curve like this, A to B, let's think how to find this area. I don't have a formula for a curve. We know, for example, the area under a trapezoid, or for a trapezoid, for a rectangle, for a circle. These are we have formulas for non-geometrical shapes, but for an arbitrary curve like this, we don't have a specific formula for it. So how would we find that area under the curve? There is a scientist in 18th which is called Leibniz, and he was in the meanwhile with Newton, Isaac Newton. Okay, they both established the science of calculus, differentiation and integration, but Leibniz was a scientist, was more had a more mathematical orientation. Isaac Newton had more a physical orientation, but Leibniz had a more mathematical orientation. So his expressions for the integration and the differentiation were best, or were better than was that of Newton's. Okay, so until now we still use the symbols and the terminology that was used by Leibniz. Okay. Do you know this symbol, for example, for the slope of tangent, that was used by Leibniz? Okay, so how can we find? Let's think as Leibniz did to find the area under the curve. Okay, so Leibniz thought like that. He thought that if we divided that area to many areas like this, okay, small areas like this, and every strip of that had a width, a small width. He called that small width, he called it dx. Okay, now what is the length? The length will be f of x. Okay, so if you need to find that area of that strip, first, what is dx? What is dx? Dx is delta x, but it is approaching 0. What do we mean by approaching 0? It is not a number. Do you know infinity?
Yeah.
Do you know infinity? Infinity is not a number. It is something that is dynamic. It just increases infinitely. Yeah, it doesn't. It is not static. So I can't treat it as a number. That also happens for this. For this number. This number is called infinitesimal. Infinitesimal, which is just the opposite of infinity. Infinitesimal is the opposite of infinity. Okay? It is a number that 0. It is a number that approaches 0, but it is never 0. How is that? Delta x, we can say that for delta x approaching 0, we can say that it is 0.00000 with infinite number of zeros than 1.
Kind of limit.
Yes, kind of a limit. It is never 0. It is never exactly 0. But at the same time, it is dynamic. It is just getting smaller and smaller each time. As infinity, it gets larger and larger each time. It gets smaller and smaller, but it never gets to 0. Okay, so that is meant by infinitesimal, and he symbolized that expression with dx. So what is dx? It is an infinitesimal number that is approaching 0. So he assumed that to find the area, he assumed that the width is infinitesimal. In that case, what is the area of that red strip? The area will be f of x that can be approximated as a rectangle. Okay, a very small width with a length. So we will multiply both of these, f of x dx. That is called, he called that dA. dA, that is also an infinitesimal area. If you multiply this infinitesimal value multiplied by f of x, you will get also an infinitesimal value. So he symbolized that by dA. Okay? Which is d area, d of the area, or infinitesimal area. Infinitesimal area. Okay? But he wants the total area under the curve. So what is the total area under the curve? He said that we need to sum dAs, all these dAs, like this, like the red one. He has many of this. Yes, we will sum all of these dAs. Okay? When we sum all of these, do you know this symbol?
Yes, summation.
Yes, this is summation. This is a capital S in Latin. Capital S in Latin come from the word sum. So Leibniz chose another word for this case. He chose that symbol that is a letter S, but it is just
extended.
Yes, extended like this. That is a letter S, comes from sum. Okay? So it is the sum of dA. What is the area? The area or the total area is the sum of dA. What is dA? It is this expression. So from that he got that expression for the area, the sum of the d area, or in sum of f of x dx. Okay? That is summed from a to b, from that value to that value. Okay? So that is the area under the curve. For now, we just expressed the area under the curve with that symbol, but how can we get the value of that area? That is the question. How to find the value of that integration? Now look how did Leibniz thought about it. Look at this expression. dA is equal to f of x dx. Okay? Let's divide both sides by dx. So we'll get that dA by dx is f of x. What do we mean by this expression? That the derivative of the area is f of x. So if we need to find the area, we need to find a function that if you make a differentiation for it, you will get f of x. That is exactly the inverse definition of the derivative. How? You are looking for a function that if you differentiate it, you will get f of x. Do you know when I say, what is the square root of 4? What is meant by square root? A square root is the inverse of squaring. It is, we are finding the value that if you square it, you will get 4. Okay? That is the same. It is just the same meaning here. If what is the area, what is the function that if I differentiate it, I get f of x. So how could we find this value? We find it by looking for a function that if I differentiate it, I get that function. Let's look for an example. If I say I need to find x power 3 dx, I need to find that integration. So I'm looking for a function that if I differentiate it, it gives me x power 3. Now I know if I make a differentiation, the power goes down, and if I make a differentiation for x power 3, how can we make a differentiation for this? How to differentiate it? The 3 goes on the line, then we subtract 1 from the power. Okay? So I need a function. If I differentiate it, I get x power 3. It is obvious that this function will be x power 4. But if I make x power 4, if I differentiate it, I will get 4 x power 3. No, I just need it to be x power 3 only without this 4. So what would I do?
Divide.
I will divide both sides with 4. So what is, I will call it the antiderivative of x power 3. What is the antiderivative of x power 3? What is the antiderivative of x? It is x power 4 over 4. That is the function. If I differentiate it, I will get that function inside the integral. Okay? So now let's learn. We need to learn now how to integrate functions. How we will do that? We must know first that integration is not straightforward as differentiation. Differentiation, we had some rules, a table and some rules. If we apply the rules for the table, we will get the value. Okay, that was differentiation and it was straightforward. Whatever was the difficulty of the problem, I can solve it. We have a table and we have rules. I will just apply it. If it is applied correctly, I will get the correct answer. Okay, this is not the case in integration. Integration, you can consider it as an art. Why? Because you are looking for something. If you differentiate it, you will get the function you will find. So what we will do, we will take some steps that make it easier for us to find that function or the antiderivative. For example, we looked for this. We found it by inspection. We just looked for a function that if I differentiate it, because I know the rule for differentiating x power n or the power function, by inspection we made some rule for this. So let's write the rules that come from making inverse for the differentiation table. Okay, we learned before that d by dx of x power n is n x power n minus 1. That was the rule of differentiation. That's inverted. I will take the integration both sides, so I will just say that integration of x power n, I'm looking for a function that if you differentiate it, you get x power n. What is that? We learned here, for example, that it has a power that is plus 1 for the given power. So it is x power n plus 1. If I give you integration of x power n, it is x power n plus 1. And we divide by n plus 1. Okay? There is another term which we'll call plus c. Why do we put plus c in any integration? Because the derivative of any constant is, what is the derivative of any constant?
0.
It is 0. So any given function, you can consider it as integration of f of x plus 0. Any function can be considered as a function plus 0. What is the integration of 0? It is constant. What is the function? If you differentiate it, you get 0, it is a constant. So any integration has this arbitrary constant. The result of any integration must have this arbitrary constant. Okay? So that is the first rule in the table. Integration of a power function, we add 1 to the power and we divide by the new power. Okay? We call this the power function rule. The power function rule. You know that x power n, this is called the power function, and this is the power function rule. Okay?
Okay.
A special case for integration of 1 over root x. 1 over root x, it is x power minus half. So what is the antiderivative of this function? Let's apply the rule. It will be, I will add 1 to the power, so it will be x power
Plus
1 half, yeah, over 1 half. That is exactly 2x power half, which is 2 root x. Okay, and that is a known rule that will be memorized because we'll use it much. It will be 2 root x like this. Okay, so the integration of 1 over the root is double the root. Okay, now remember that this rule just applies for square root in the denominator. It doesn't apply for 1 over cubic root of x, for example. No, for this case we just apply the rule as it is. I will just say it is x power minus 3, and then I add 1 for the power and divide by the new power. Okay? Also, what is the integration of root x? Would I say 2 root x or 1 over 2 root x? No. This rule we apply it as it is. It just must be in that same form, 1 over root x. We apply that formula just for that, exactly that form. If it's just different slightly, no, I wouldn't apply the rule. Okay, we'll learn to treat problems exactly as given, and we will extend our skills one by one until we find or can solve more problems. Okay, so how can we find this? We just apply the power function rule, which will be that is x power half. So we add 1 for the power and divide by the new power. Okay, so that is the power function rule. What about integration of x power minus 1? Or that is integration on 1 over x. What is the function that if you differentiate it you get 1 over x?
ln.
Yeah, ln, yes, that is ln x. That is ln x. Okay, so why? Because if you differentiate ln x you will get 1 over x. We'll just make a slight generalization for this rule. We say that it is ln absolute x. It has a proof. We have a proof that if you differentiate ln absolute x you will get 1 over x. Okay, and this can be applied for x positive or negative or any value of x. So you remember that ln doesn't take a negative input, but now we have ln absolute x. So whenever I have a negative value, it is inside an absolute value, and it will be a positive again. Okay, so that is the power function rule. That is the first rule. That is the second rule, which is of the ln. Okay. We have the rule of the exponential e power x. We learned that the differentiation of the exponential is exactly the same exponential, and that will be the case here. So that it will be like this. But if I had a power x dx, okay, do you remember how to differentiate a power x?
Yeah.
It was the same. If I have an exponential function, that is called an exponential whenever I have a constant power variable. We have here that is called an exponential function. Okay, so differentiation of an exponential function is an exponential function, but we may multiply by some other things. Do we multiply by ln of the number that takes the place of e? Any number that takes the place of e, we multiply by ln a. Also, we multiply by the derivative of the power, and that is another case. But for this case, a power x dx, it is exactly a power x. But in this case, instead of multiplying by ln a, we will divide by ln a. Why? Because if you differentiate that expression, you will need to multiply by ln a, so they can be cancelled, and I will get a power x. Okay. Now I will do the same for all the table of the differentiation, all the expressions. We will just make the same as we did. We'll find the answer. We will just invert it. Okay. So let's write the trigonometric functions table of the integration of trigonometric functions. Integration of sine x, integration of cosine x, integration of sec squared x. I will not write integration of tan x, no. I will write integration of sec squared x. Why? Because I got it from the table. Yes, the table, the function that if I differentiate it, I will get tan.
And in such a question, in like when they give me an equation with the tan, integration of tan 1
yes, we will find how to find this. But now, just as I told you, we learn it a bit by bit. We take something and then we extend our skills. Okay, so we are limited for certain types of problems first, then we extend it one by one. So it is an art. We just learn how to make this. Okay, so we have some expressions that we know its result. We just need to first learn those. Then, if I have an expression that is not inside the table, how would I treat that problem? We will learn that. Okay. Also, we have integration of cosec squared, integration of sec x tan x, integration of cosec x cotan x. That is cosine x plus c, but we will have a negative value here. Also, this is sine x. That will be tan x. That will be negative cotan x. That will be sec x. That will be negative cosec x. Okay? Now, I just need to note that I had a negative value whenever was the result had a co. Whenever the result had a co. If you remember from the table of differentiation of trigonometric functions, whenever the function has a co, the result had a negative. Okay, in differentiation, if I told you find the derivative of cotan x, that was minus cosec squared. Why is this minus? Because I have co in this function. Now I'm not looking for the co here. No, I'm looking for the co in the result. If the result had a co, then we put a negative sign. Okay? So these are the rules of trigonometric functions. Similarly, we'll just write the table of hyperbolic functions. In hyperbolic functions, the derivative of hyperbolic functions was the same as the derivative of trigonometric functions, but except with just one exception, that the signs, if I make a derivative d by dx of the three basic functions, which are sine, cosine, and tangent. These are the basic three functions. Then we have the reciprocals of them. We have cosec, and we have sec, and we have cotangent. These are called the reciprocals of the standard hyperbolic functions. We learned that the derivative of reciprocals has a negative. Now we are not looking for the co or not co. No, we are looking at if the function is a reciprocal or not. If it is one of the basic functions, we don't put the derivative will be positive. If the function is a reciprocal, then we put a negative value. In the integration, when we generate the integration of the integration table, instead of saying if the result has a co, we put negative. No, we say if the result has a reciprocal, we put a negative. Okay, so let's type this: integration of sine x, integration of cosine x, integration of sec squared x, integration of cosec squared x, integration of sec tangent integration of cotang x. We have the same rules as trigonometric functions. Cosine is sine. The integration of cosine is sine. The integration of cosine is integration of cosine no, this is sine. The integration of sine is cosine. The integration of cosine is sine. The integration of sech squared is tanh. The integration of cosech squared is cotang. The integration of sech tanh is sech. The integration of cosech cotang is cosech. Now we look at this expression. If the result had a reciprocal, we put a negative sign. So that is, no, these are the basic functions. But cotang is a reciprocal, so we put a negative sign. Sech is a reciprocal, we put a negative sign. Cosech is a reciprocal, we put a negative sign. Okay? So these are the rules of hyperbolic. In this side we have the hyperbolic, and in this side we have the trigonometric. Okay? So this is the tables. These are the tables of trigonometric and hyperbolic. It remains to generate the table of the inverse trigonometric functions and inverse hyperbolic functions. Do you remember if I told you I need to find d by dx of sine inverse x? Do you remember that expression?
Yeah.
That was 1 over root 1 minus x squared. Yes. Okay. Now let's invert it. Now in this case, if it means that the integration of 1 over root 1 minus x squared dx, that will give me sine inverse x plus c. Okay, I just inverted that rule in differentiation. And also we learned that d by dx of tan inverse x. Do you remember the rule? 1 plus 1 x squared. Okay, so I just write that 1 plus 1 x squared, it will give me tan inverse x plus c. Okay, let's write all the other rules. We have another rule which is dx x root x squared minus 1. That gives me sec inverse x plus c. And we also have the inverse hyperbolic functions. That is integration of 1 plus x squared. Look, it is just looks similar to this, but instead of the negative here we have a positive. In that case the result will be sine inverse x. Okay, I may write it like this. If I put a positive here, it will be for the blue. If I had a positive, I will get sine inverse. If I had a negative, which is black, I will get sine inverse. Okay? But I'll just erase it so I don't make any confusion. Also, look at this expression. If instead of the plus I wrote 1 minus x squared, let's write it. Integration of 1 minus x squared. That will be tan inverse x. Okay? So in this case, if I put positive instead of negative, I will get sine inverse. In this case, if I put negative instead of positive, I will get here tan inverse. Okay? So these are two basic, or I can consider them as 4. Okay? These two, which come from these two rules, I inverted them. Then I learned that if I change the sign, I will get the other side. I will make it hyperbolic. Okay? Just there is still one case that we didn't consider here, which is
cosine.
Yes, the cosine inverse. The cosine inverse. Cosine inverse. There is another rule. If I had integration of dx root x squared minus 1. X squared minus 1. In that case, that will be cosine inverse x plus c. Okay? So these two rules are two basic rules. If I change the sign, I will put hyperbolic. That rule, I remember that rule from x squared minus 1. It gives me an indication as if x has a large value here. If I say x squared minus 1, it is inside the root, and I can't have a negative value inside the root. So that x squared cannot be smaller than 1. It must be greater than 1. So x is a large value. Look at this expression. This expression means that x must be a small value, smaller than 1. Why? Because I take here 1 minus x squared. 1 minus x squared, and this is a small value, so that there is no negative value inside the root. Okay? In this case, it indicates that x has a large value, a value larger than 1. Okay? A value larger than 1 reminds me of cosine. If you remember from hyperbolic functions,
It was like
yes, the cosine x was the largest of the hyperbolic functions. Cosine, the function of cosine, was the largest between the hyperbolic functions. Okay, it is larger than sine, it is larger than tangent, it is larger than all of them. The largest of them is cosine. Okay, so I just remember when I have if x squared minus 1, it reminds me, yes, that is the inverse of the greatest of the cosine of the hyperbolic functions, which is cosine x. Okay, so these are the two basic rules with changing the sign and plus this one. We can add also this one of the sec inverse, but it is rarely used. This rule is rarely used. We have these two and the other analog two rules for the hyperbolic plus this one, so we have 5 important rules plus one that is of the sec inverse. Sometimes we need it, but not
so much.
Yes, not so much. So that is, now we have just generated the integration rule, the integration table. The first skill that we learn, or the first rule that we learn, that integration is linear. Integration is linear. What do we mean by that? If I have a f of x plus or minus b g of x, as just in differentiation, the integration may be distributed like this. So I can say that it is integration a f of x plus b g of x. Okay, we call this property, it is linear. It can be distributed like this. And also we can take the constant out of the integration. So we'll say a integration of f of x plus b integration of g of x. Okay? So we can put a new rule for us. I may have a function that is not inside the table. This function may not be inside the table. Okay? But if I distribute it like this, and I find that each of these is inside the table, then I have solved the original problem. Okay? So what is the first skill that we learn in integration? If I have a function, I just look. Is it inside the table? Yes, okay, then I will apply the rule. If it is not inside the table, I will just, from my mathematical skills, try to put it as addition of rules that are inside the table. Okay? What do I mean by that? For example, if I have this problem, integration of 2x cubed plus 4 over root x. This is not inside the table. Okay, I just have this rule, integration of x power n dx. That is the power function rule. But this is not in that form. But I learned that for this expression, I can make a step that makes that expression expressed as a sum of two forms that are just like that form. We learned that we can distribute this like this. So it will be integration of 2x cubed over root x plus 4 over root x dx. I have just distributed these two, okay? And that will be 2x power 3 minus half will be 2 and a half, which will be 5 over 2, and that will be 4 over root x, like this. So both of these terms is inside the table. In this case, both of the terms are inside the table. So I have managed to solve the problem. The original problem was not inside the table, but when I worked on that and I made it as a sum of expressions that are inside the table. Okay, we'll just apply the rule for each of these terms. So that will be 2. I just add 1, the power function rule. I will just add 1 like this and divide by the new power. And for this case, we'll just put 4 as it is. 1 over root x, we just learned that it is double the root. Yes, double the root, and then I say plus c. Okay? What if the problem was like this? Instead of this, it was root x over 2x cubed plus 4. X cubed.
Try to do the same thing.
Yes, we'll try to do the same thing. The same thing, which we will distribute it like this. It will be root x over 2x cubed plus root x over 4.
Okay.
Is that correct?
No, I don't think so.
No. That is a fatal mistake. That is a fatal mistake. I never say that I can distribute the numerator on the denominator like this. We just make it if I had the denominator had the one term and the numerator had several terms, I can distribute it. Yes, I can distribute this, but I don't make the opposite. Okay? So in this case, I can't say how can I solve it now. Okay? But I cannot, I insist that this is never solved by making it like this. Okay?
Okay.
For example, if I had integration of x squared minus 4 all squared, this expression is not inside the table. But how can I manage to make it as the sum of terms that are inside the table?
I'll try to look. This is the two expression. I'll try to.
Yes, we'll try to expand it. We can expand it. We know if I had a plus b all squared, it will be the squaring of the first, double the multiplication, then the squaring of the second. So I will just expand it. That will be x power 4 minus double, that will be 8x squared plus the squaring of 4, which is 16. Okay? Now, that original expression was not inside the table, but I managed to express it as sum of terms that each of them is in the table.
In the table.
Yes. These are power functions, so I just apply the power function rule. That will be, I just add 1 for the power and divide by the new power. 8x cubed over 3 plus 16x plus c, like this. Okay?
Okay.
What about this problem? If I had integration of 3 power x root e power x. This expression is not inside the table, but I learned that it just reminds me, as I have here exponential functions, I have here x in the power and the number in the base, so it reminds me of this rule, which was a power x over ln a. It reminded me of this rule, but for this rule I just need to apply it as it is. The problem must be in exactly this form, a constant power x. To apply the rule, we just need to be just exactly the same. For now, if I just change it to be x squared, no, I can't apply the rule. If I put 2x, no, I can't apply the rule. I just need to make it just exactly as the rule. Now, For the mathematical skills that I've learned before, can I manage to put this in the form of a constant power x or not?
Yeah, you can.
Yes, I learned before that I can say if a power x, b power x is, I say that this is ab all power x. And also if I have a power x all power y, that is a power xy, and which is can be also written as a power y power x. These are all the same. So for this case, let's look at this one. I will just can write it 3 power x, and here I can apply this rule. It will be e power
Half times.
half, yes, half, which is root all power x. What about this? Is it the same?
Yes, the same.
Yes, it is the same. Now I can apply this rule, because now I have same powers and these are constants. So I can say that this is just 3 times root e all power x. Now I have, now can I apply the rule, can I apply this rule on this expression or not?
Yeah, now you.
Yes, it is a number power x, which is exactly the same form that we have told here. Okay, so that will be the same expression, which is 3 root e. Then I divide by ln of that number. Then it will be ln 3 root e like this, plus c. Okay?
Okay.
Now if I had an expression like this, integration of sine x over 2 cosine x over 2 dx. This expression is not in the trigonometric table, integration table. I have only sine x, cosine x alone. Sine x alone or cosine x alone. But I don't have sine x multiplied by cosine x. So what did I learn? A formula that converts this into a single expression with sine or cosine?
Yeah.
Yes. What was it?
It was a sine 2x.
Yes, it is the sine of the double angle is exactly double sine x cosine x. So I can say that sine multiplied by cosine is half sine double of the angle. Okay? So I can say here that this is half sine double of the angle, which is x. Now this is an expression that is inside the table. Now I can solve it, and I will say that this will be cosine x plus c, and because there is co in the result, I will put a negative sign. Because I had a co in the result, I will put a negative sign. Okay?
Okay.
Also, if I had integration of tan squared x, tan squared is not in the table, but I have something maybe near to tan squared, which is sec squared. I have a rule for sec squared, it is tan.
Yeah.
Can we find a formula to express tan squared in terms of functions that I know its integration?
Yeah. The basics rule of
Yes, the basic rules. We know that tan squared is sec squared x minus 1. Sec squared and cosec squared are the largest of the trigonometric functions, so we subtract 1 from them to get the tan or cotan. We know these two rules, that tan squared is sec squared minus 1 and cotan squared is cosec squared minus 1. So in this case, now we express tan squared as the sum of two functions that are inside the table. Sec squared, the integration of sec squared is just tan x minus 1. What is the integration of 1?
x.
Yes, it is x. Integration of 1 is x. Why? Because 1 is just x power 0. If I add the power 1 and divide by 1, which is just exactly x. Okay? So this is the result of that integration. Now if I had, for example, integration of sine squared x over 2. Sine squared is not in the table, and learn that I cannot say, for example, I know that integration of cosine x is sine x. I know that in the table, from the table. Can I say that integration of cosine squared is sine squared? Can I say that? No. This is a rule from the table. Some students can say that I can make power 2 for both sides. No. Integration rules are treated as they are, without any change. Okay? We just extend them a bit by bit by known rules and restrictions. Okay? And we cannot make a power by itself, for it is not like in any equation. For any equation, I may say if this is equal to this, I can make squaring both sides. Okay, that is allowed. But for the integration, no, I can't say that. Okay?
Okay.
What I need to think for this problem, how would I manage to solve it? I will just look for rules that I learned to express that in terms of functions that are inside the table, which are cosine and sine. And we have these rules. These rules are that cosine
squared equal
cosine squared x is equal to half 1 plus cosine double the angle. And we have sine squared x is half 1 minus cosine double the angle. Okay? And I will also put with them that rule. If I had sine x times cosine x, it will be half sine double the angle. These two rules are very important. These three rules are very important for us. Why? Because they convert second degree trigonometric functions in terms of first degree trigonometric functions. That's why they are important. Many of the mathematical rules are based on cosine or sine power 1, not power 2, not power 3, or so on. So if I had a rule like this, cosine squared, sine squared, and it converts to, or it can express it as a linear combination or a sum of power 1 cosine and sine, so that is a very huge advantage for us. Okay? And that's also the case for this expression. Sine x times cosine x, we call it as a second degree. Why? Because we consider sine and cosine at the same difficulty if we multiply them as if they are second degree. And this expression also converts a second degree expression to a first degree one.
okay.
Okay? So what we'll do in this problem, sine squared will not square the result. Now we just use one of these rules to express it as cosine and sine but power 1. Okay?
Okay.
So sine squared, we'll apply the rule. Sine squared is half 1 minus cosine double the angle. What is double angle? It is x.
And from there it's very
Yes, now it is very easy. It will be x minus sine x all plus c. Okay?
okay.
What about this expression? Now, as you are seeing here, we are just seeing problems with my learned mathematical skills. I apply them so that the given expression, although it is not inside the table, I will just manage with my mathematical skills to convert it to a sum of terms that are inside the table. Okay? Now let's see this problem. For this problem, x squared 1 over 1 can x squared over 1 plus x squared over x squared, which will be, these two terms are,
Is that possible?
no, yes, you are correct. This is wrong. That is a fatal mistake. Again, I put your attention that it is not possible to make this expression. So what is possible for an expression like this? We have two methods. One method, and this method is applied whenever I have a polynomial over a polynomial. If the degree of the numerator was greater than or equal to the degree of the denominator, you know that the long division will always make the problem simpler. Whenever I have the degree of the above is greater than or equal the degree of the below. Okay? But just in this case, especially in this case, we can make a trick. Look, what will I do? What if I say, if I add 1 and subtract 1 and treat that as a bracket?
Okay.
Now I can distribute this like this. So I will have 1 plus x squared over 1 plus x squared, which will give me 1, minus 1 over 1 plus x squared. Now look at this expression. Yes, this will be x. What about this?
Tan
Yes, that is tan inverse.
inverse.
So we have managed to solve the problem. Okay?
Okay.
So one of the main skills that I should have, that I must detect whenever I have a rational function. What is a rational function? If I have a polynomial over a polynomial. Okay? Whenever I have a polynomial over a polynomial, it just reminds me of the long division or an equivalent form that I add and subtract some terms that will make the problem simple. These two methods are equivalent. Let's solve it again, but by long division. And you must learn how to make long division.
Okay.
You must learn, it is obligatory to know how to make long division. How would I make long division for this problem? I just detected that it is a polynomial over a polynomial, and I detected also that the degree of the numerator is just exactly the degree of the denominator. So I learned or I have known that I can use long division. Okay, so let's make long division in this problem. I write x squared here and I write x squared plus 1. Now look that I ordered them in descending order. Okay, I didn't write it 1 plus x squared. I wrote it x squared first, then 1.
Okay.
Starting from the largest power to the less power. Okay, with this order. Now how to make long division? It is an easy and systematic approach. We divide the largest power term to the largest power term. Divide only these two terms, the largest power term with the largest power term, which is x squared divided by x squared will give me 1. Okay? Then in this case I will multiply 1. That result I will multiply it to all of this. It will give me x squared plus 1. Then in this case I will subtract. Okay?
Okay.
I will make a subtraction. And always I will find that this term is cancelled with this term. Always I will find that this term is cancelled with this term. Now 0, negative 1 will give me negative 1. Okay? Now I may have an expression here. If that expression had a degree that is larger than or still equal to that degree,
No.
I will continue or I'll make the same I will make the same steps that I did from the first, and we'll see another example in this case. But in this case, we had the result. That degree is 0 degree. It is a constant. It has a 0 degree. And that is second degree. Whenever I had a result here that is less, with a degree that is less than this expression, then I stop. Okay? Now I need to write the result of this. I learned from this that x squared over 1 plus x squared, its result is this one. It is 1. That's the result. Okay? This is the remainder. Yes, that is the remainder, which is negative 1 over, if I had to complete, I will just divide this by this. And that is what I will write here. I will just divide this by this. It will be x squared plus 1.
Okay.
Look at this. This is exactly what we have written here. 1, but I just had this sign. It was here. This is exactly the same. That's why I told you that these two methods are equivalent. Okay?
Okay.
The long division method is maybe applied for many forms, or for many, but this case is just a special case. Add 1, negative 1, add 1 and negative 1, then we can manage to find an expression which is equivalent to the long division. But mainly the method of solving this type of problems is long division. Okay?
Okay.
Let's see this problem. If I had integration of x power 4 over x squared plus 1. I just detected that it is a polynomial over a polynomial. Okay? I check, is the degree of the numerator larger or equal to the degree of the numerator?
And then
is it larger or not?
It's larger.
It is larger, so I use long division. Long division. That detection is a skill. Remember, whenever I need to be skilled that I detect this expression. Okay? Detect a polynomial over a polynomial. And I know or decide if I can use long division or not. Okay? Now for this expression, I will use long division. Let's make the long division in this case, which is x power 4 over x squared plus 1. I just wrote it like this. Now let's make the steps of long division. I divide the term of largest power to the term of largest power, which is x power 4 over x squared, which will give me x squared. Okay? Now I will multiply this term to all of this, which will give me x power 4 plus x squared. Then I subtract. Okay, this is cancelled with this, and we have here 0, negative x squared, which will give me negative x squared. Should I stop here?
No.
No, because I have the degree here is exactly the same degree as this. So what will I do? I will just repeat the same steps again, as it was the beginning of the problem. Okay, I will just divide the term of the largest power to the term of the largest power. I may have some other terms here, but I divide the term of largest power to the term of largest power. Okay? That will give me negative 1. Then I will multiply that negative 1 only, not all of this, only that term. I will multiply it like this. So it will be negative x squared negative 1. Then I make a subtraction. That term will be cancelled with this one. Then I will have 0, negative 1, which will be positive 1. Now should I stop here?
Yeah.
Yes, I will stop here. Now I'm ready to write the result. The expression for this. The expression for this is, that is the result of the division. X squared minus 1. That is the remainder. That will be 1 over
2 squared plus
x squared plus 1.
S squared.
Okay?
Okay.
Can I make an integration? Yes, all of these terms are just inside the table. So we'll have this will be x over power 3 over 3 minus x plus tan inverse x. Okay?
Okay.
Now what about this expression? This expression is not inside the table, but I try to make simplifications to be written to see if it is can be written as a sum of functions inside the table or not. Okay?
Okay.
This expression can be written as sine x over cosine squared x.
Okay.
And this also can be sine x over, I will take one cosine like this, times 1 over cosine x. I can easily detect that this is just tan x and this is sec x. This inside the table? Yes. Sec times tan is inside the table.
Yeah, it's inside.
Yes, it is inside the table, and that will be sec x. Okay?
Okay.
At first, you should have the table of the integration before you as you solve. Then you will memorize it with practice. Okay? We will see another two tricks that we can do. If I had, for example, dx over 1 plus sine x, 1 plus sine x in the numerator. Now we learned that we cannot distribute it. I can say, I see some students that do that fatal mistake. This is wrong. Okay? Now, what could I do in this case? There is a trick or a skill that we'll know, that we sometimes can multiply in the numerator and denominator with the conjugate of the expression given here. That will be 1 minus sine x, 1 minus sine x. I didn't change the function because I just multiplied yes by 1. But what is the advantage of multiplying a bracket with its conjugate? If I had a plus b times a minus b, what is the result of this expression?
It's going to give us in square.
A squared, yes, the difference of squares. Difference of squares. This is a known expression. So that's why in this case 1 plus sine, 1 minus sine, when multiplied it will be 1 squared minus sine squared. And for the numerator we'll have 1 minus sine x. Now I need to remember that there is, I told you that we cannot have explicit rules for integration, but there are some rules that give us some guidance or makes the problem simple. One of the main rules is that in integration in general is that we like to make the denominator to be one term. We need to squeeze the denominator to make it one term, and we need to expand the numerator. Okay? I'm guided to this, oriented to make it like this. We make an advantage if I made the denominator smaller or having one term, just one term, and expanding the numerator. Okay? Look at this expression, 1 minus sine squared. What is 1 minus sine squared? Did I learn anything that?
Yeah, the first rule of trigonometry.
Yes, it is. That is cosine squared. Yeah. We learned that cosine squared plus sine squared is equal to 1. So I can express any of these, which would be 1 minus sine squared is 1 minus cosine squared. Well, sine squared is 1 minus cosine, and so on. Okay? So that's why 1 minus sine squared is exactly cosine squared. Now look for this expression, that is 1 minus sine x over cosine squared x. I just need to detect this or to observe this, that we managed the original problem had two terms in the denominator, but from my mathematical skills and by the multiplying with the conjugate, we managed to make the denominator to be one term instead of two terms, and that is an advantage for us. Okay, now I have managed to make it one term. Okay, let's distribute it. So that will be 1 over cosine squared, that will be sec squared, minus sine over cosine squared.
Tan is going to be tan
times sec. Yes, that will be minus tan times sec x. It will just be like this. And these two are inside the table. These two terms are inside the table. So that will be tan x minus sec x.
Okay.
So we managed to make this. We can apply this conjugate rule whenever I have an expression like this and I know there is some rule for the squaring minus square. Okay, I just looked at this. If I had, for example, 1 plus cosine x, I know that squaring of this minus squaring of this it will squeeze the denominator. So I can apply the conjugate rule here, or the conjugate method here. Okay?
Okay.
And so on. For example, if I had tan x plus sec x, or sec x plus tan x, it doesn't matter. Sec x plus tan x. This, I will just look at this. I try to multiply it. I just observe that squaring minus squaring, which is sec squared, minus tan squared, it will just give me sec squared minus tan. I have a rule for this, which is 1. So it is obvious here that this integration will be easier if I multiply by the conjugate in the numerator and denominator. Okay?
Okay.
Maybe we couldn't complete it, or what we have learned for now, we couldn't complete the problem, but we just know that it could be easier if we squeeze the denominator in some way. Okay?
Okay.
Okay, just let's